Hello everyone. In this video, we are diving into a powerful yet simple data type in Python, Booleans. These are used to represent true or false values, and they help us make decisions in our code, especially when we filtering or flagging bioinformatics data. What is a Boolean? Booleans or bool in Python can only be one of two values, true or false. You will use them all the time to write logic like checking if a mutation passed a quality filter or if a read depth is high enough. Now let's switch to Jupyter Notebook and see how to use booleans with simple bioinformatics examples. Let me first add a markdown title defining booleans in Python. Here I am writing a comment that says, was the variant found? Comments help us explain what the code is doing. Variant underscore found equals to true. Here I am creating a variable called variant underscore found and setting it to true. This might mean that a variant was successfully detected in a sequencing result. Now I am writing a comment, is the sequence high quality, to describe what the next variable is about. High underscore quality equals to false. Here I am creating another boolean variable called high underscore quality and setting it to false, meaning the sequence didn't pass our quality filters. Print variant underscore found and print high underscore quality. Here I am printing both variant underscore found and high underscore quality so we can see their values. And we get true and false just as we defined. These flags are simple but very useful in bioinformatics pipelines. When do we use booleans? You will use booleans in filtering reads, checking conditions, and writing if statements. They are behind every decision your code makes. Now let's jump to the Jupyter Notebook and explore Boolean expressions. These are comparisons that evaluate to true or false. Let me first add a markdown title, Boolean expressions in bioinformatics. Here I am writing a comment that says, check if read count is above threshold. Read underscore count equals to 120. Here I am defining a variable called read underscore count and setting it to 120. This could represent the number of reads aligned to a gene. Is underscore high underscore coverage equals to read underscore count greater than 100. Here I am checking whether read underscore count is greater than 100 or not and storing the result in is underscore high underscore coverage variable. The result will be a boolean, that is, it will be either true or false. Print is underscore high underscore coverage. Now I am printing is underscore high underscore coverage to see whether the condition evaluated to true or false. Since read underscore count is 120 and that's more than 100, the result is true. That tells us this region has high coverage. Next, I am adding a comment that says check if sequence length is equal to expected length. Observed underscore length equals to 1500. Here I am defining a variable observed underscore length and assigning it the value 1500. This might be the actual length we observed in our sequencing data. Expected underscore length equals to 1500. Now I am defining another variable called expected underscore length also set to 1500. This could be the reference or expected gene length. Length underscore match equals to observed underscore length double equal to expected length. Here I am checking whether the observed length matches the expected length using the double equal to operator and storing the result in length underscore match variable. Print length underscore match, and here I am printing the value of length underscore match to check whether the two lengths are the same. Because both lengths are 1500, the result is true. This tells us the observed sequence is the correct length. Here I am writing the comment was the quality above threshold. Quality underscore equals to 28. Here I am defining a variable quality underscore score and setting it to 28. This could represent a Fred quality score from a sequencing read. Passed underscore quality underscore filter equals to quality underscore score greater than equal to 30. Here I am checking whether the quality score is greater than or equal to 30 and storing the result in passed underscore quality underscore filter. Now I am printing passed underscore quality underscore filter to see whether this sequence passed the quality threshold or not. Since 28 is less than 30, the result is false. That means the read did not pass the quality filter. Now I am writing the comment combine Boolean conditions. We are going to check two conditions together. Depth equals to 45. Here I am defining a variable called depth and setting it to 45. This might be the sequencing depth for a given region. Quality equals to 35. Now I am defining quality and setting it to 35. This is the same kind of quality score we used earlier. Pass underscore filter equals to depth greater than 30 and quality greater than 30. Here I am combining two conditions using the AND operator. One checks whether depth is greater than 30 and the other checks if quality is greater than 30. Both must be true for pass underscore filter to be true. Print pass underscore filter. Now I am printing pass underscore filter to see if both conditions were met. Since both depth and quality are above 30, the result is true. This read passes our combined filter. Why Booleans matter? Booleans are how your code make decisions. Want to keep only the variants with quality above 30 or check if a sequence is aligned properly? You will need Booleans. So to recap, Booleans are simple true or false values and they are everywhere in bioinformatics, filtering reads, checking QC, or even just building conditions for automation. Thanks for watching. If this helped you, hit that like button, share it with a fellow bioinformatician, and don't forget to subscribe to the channel for more Python plus bioinformatics content.